Hello again, Physics 20s. In today's lesson, we are going to talk about a physical quantity that is called work, and then we're going to look at how it can be calculated and different scenarios where work can either be positive, negative, or equal to 0. Learning outcome is to 1. Recall work as a measure of the mechanical energy transferred. So work, which we're going to use the variable capital W to represent, is a measure of the amount of energy transferred from one object to another. More specifically, when you do work on an object, you transfer mechanical energy from one object to another one. However, I'm not going to worry too much about mechanical energy just yet. We'll actually define it in the next lesson. We're going to worry about more so today is what do you need to do to actually do work and transfer this energy. It turns out in order to do work on an object, you first of all need to exert a force on the object and you need to get it to move. So there must be some kind of displacement of the object. I'll draw a small illustration here. So let's say that you have a box and I'm going to pull this box at an angle above the horizontal with a force F. We'll call this angle above the horizontal theta. If you apply force to this box and you can get it to move, so let's say we're on a flat surface, my displacement would just be horizontal, then you would do work. And when you do work on an object, you transfer energy into it. If this box was at rest initially, it would have no kinetic energy. Kinetic energy is energy of motion. Again, more to come on that later. However, by applying a force and moving it, you're definitely transferring energy into the object because you're then getting it to go from not moving at all to moving it at some kind of speed. To calculate work, we use the following equation. This is the general definition of work. We have work is equal to F and dot D. The dot is something called a vector dot product. Vector dot product is something that you would learn more about if you take a linear algebra course or advanced placement physics at the 30 level. All we need to worry about right now is what a vector dot product expands to. And a vector dot product expands to, in the case of work here, work is equal to the magnitude of your force multiplied by the displacement of the object times cosine of theta. Going back up to my up illustration of the box. So you can just think about for a second, like, in what situation do you not do any work on the object? Well, if you don't apply a force, there's absolutely no chance you can displace it. So in that case, there'd be no work. It is also possible to apply force on an object, and no matter how hard you pull on it, you cannot get it to move. Like if I went outside and I pushed on my car, it's very unlikely I could get it to move beyond just, maybe slightly oscillating back and forth. The other condition is going to deal with the cosine theta part of the equation, but we'll get into that momentarily. In this equation, theta represents the smallest angle between the force vector and the displacement vector. In the picture I've shown above, the angle theta would actually be the angle relative to the displacement vector as well. If I move the displacement vector up a little bit, then it would be right here. And we always want to measure the smallest angle from F to D. You could also measure like the angle from F to D going like the long way around, but that would not be the smallest angle, in which case we don't want to use that one. So always the smallest angle, which is going to mean that theta must always be a number that is less than or equal to 180 degrees, depending on the situation. 2, work is measured in a unit that is called a joule. And if you break a joule down into its combination units, 1 joule would be equal to 1 kilogram times meters squared per second squared. And we can derive that fairly easily. So work is measured in joules, and then force is measured in newtons, and then displacement could be measured in meters. And cosine of theta is just a ratio of length, so it doesn't have any units to it. A newton, as we've looked at in the dynamics unit, can be broken down into a kilogram times meter per second squared. And then if you just combine that with the other meters term, you would get the kilograms times meter squared per second squared. The third point describes a limitation of this equation in terms of when you're actually allowed to use it. We can only use this work equation if the force we're applying is constant. So what that means is, again, we'll go back up to my picture. If you were applying a 20 Newton force, let's say the displacement of the object was like 100 Newtons over towards the right, and over that 100 meter distance, you are always applying a 20 Newton force, you can definitely use the equation. The problem is if as you're covering that 100 Newtons, the force changes. So maybe you're pulling this box and initially like you have a lot of drive, you're pulling at 30 Newtons. And then 50 meters in, you start to get tired. So then you like reduce the force to 10 Newtons. And then near the end of the 100 meters, you're like, well, I'm almost done. So let's pull a little bit harder with 20 Newtons. Well, you have a problem now because the force value is changing to all these different numbers. And if it's changing, it would not be clear, well, what do you plug in for F? It turns out we have a workaround to deal with this when we have our force that is not constant or variable, but we'll get into that at the end of the lesson. Otherwise, there is a way to deal with this, but it does involve using calculus, which is not something that we're going to talk about right now. Again, in AP Physics 30, we do briefly touch on that. Here's the interesting thing about work. Although work is a scalar quantity, and scalar quantities only have magnitude, they do not have direction. So even though work is a scalar quantity, it can be positive or negative. It just depends on the situation. And also, the positive or negative work has nothing to do with direction. For example, if you calculated work to be positive 20 joules, that does not mean 20 joules of work towards the right. Or if you calculated work to be negative 15 joules, it does not mean 15 joules of work down. The positive and negative has some other kind of physical meaning. And we're going to address that right now. Positive work. When you do positive work on an object, you transfer energy into the object. And again, we're going to go through more classes of energy in the next lesson when we talk about kinetic energy, gravitational potential energy, mechanical energy. But you're putting some kind of energy into the object. So that example on the previous slide where a box is at rest and I pulled it, I definitely was putting energy into the object because I was able to get it to move. The question really is, to get positive work, so here's my work equation. W is equal to F times D times cosine of theta. What values of theta will actually give me a positive value for cosine of theta? Well, you need to know a little bit about your unit circle to identify this, but basically cosine of theta is going to be a positive number up to 90 degrees, but not including 90 degrees. Therefore, we do positive work on an object when theta is a number that is less than or equal to 90 degrees or greater, just less than 90 degrees or greater than or equal to 0 degrees. Again, let's just quickly draw this picture again. So if I go back to my illustration where I'm applying a force, and here's my displacement vector, and theta is this angle. As long as we could use the displacement vector as my reference angle, as long as theta is, as long as there's a component of the force here that is in the same direction as the displacement vector, you will do work. So we could actually take this vector, and if we wanted to, we could show the vector components. So we have like the horizontal component, and we have the vertical component. As long as the component of the vector that's parallel to the displacement, as long as there is a component of the force that is parallel to the displacement, then you will do work. So we would maximize this if theta was 0 degrees. Cos of 0 degrees is 1. That's the biggest value that cosine of theta can be. And then as we get closer and closer to 90 degrees, the cosine of theta is getting closer to 0. Yeah, I already addressed that. So in order to do positive work on an object, you either need your force to point in the exact same direction as the displacement, or there needs to be at least a component of your force that points in the same direction as your displacement vector. How about negative work? When negative work is done on an object, energy is being transferred out of the object. So if this man with the very stylish sweater and pants with the completely oversized pocket push that box and let go, and that box is moving at a particular speed, eventually it's going to come to rest. So if it's moving at a speed and coming to a rest, then it's losing some of its energy, losing some of its kinetic energy specifically. So what kind of force caused it to lose that? Well, it'd be the force of friction. The force of friction brought it to rest. But again, we want to look at the equation here to identify when would this be negative. So our equation is work is equal to your magnitude of the force times magnitude of the displacement times cosine of theta. And what values of theta would be negative? Well, the biggest negative number that cosine of theta can be is when it's at 180 degrees. And it turns out if you drew a free body diagram of this object here, the force of friction would point towards the left. Force of friction is always in direct opposition to the direction the object is moving. And the displacement of the object would be towards the right. Therefore, the angle between the two would just be a semicircle, which would give you a 180 degree angle. So when cos is 180 degrees, it's -1, and that would give you negative work. Therefore, negative work can occur when theta is a number that is less than or equal to 180 degrees, and that would be maximizing negative work, or greater than 90, but not inclusive of 90. And again, I know in the diagram that I showed here that the force of friction is in completely opposite in direction to that of the displacement. But if you had a force where at least some kind of component of the force was opposite in direction as d, you would again get negative work. How about zero work? Well, we already addressed this. If you never apply a force to an object, you can't do any work on it because there's no chance of moving it then. You could apply a force on an object. Again, like I could run up to a wall and do a flying drop kick, and I could apply significant force to the wall, but it's unlikely I'm going to move it at all. Therefore, I'm not doing any work on the wall. The other one is going back to our equation. So what value of theta in cos of theta would make it equal to 0? And it turns out that is when theta is 90 degrees. When theta is 90 degrees, that means my displacement vector and my force would be perpendicular to each other. So what kind of forces would do no work on the object? Well, a few of them. So my displacement vector, d, points towards the right. If I drew more forces on a free body diagram, I'd have my force of gravity that's straight down, Fg, and I'd also have the normal force that is straight up. And since the normal force is perpendicular to the displacement vector and Fg is perpendicular to the displacement vector, these two forces don't do any work on the object. Furthermore, if we look at our applied force here, if we apply force at an angle, it's only the parallel component to your displacement vector that's doing any work. The perpendicular vector to your displacement is not doing any work at all. Therefore, as the perpendicular component gets bigger and the parallel component gets smaller, you start to progressively do less and less work. The last thing comes back around to the problem dealing with the limitation of the equation. So once again, the limitation of the equation is you can only use it if the force acting on an object is constant. But let's say that the force is not constant. So this graph shows force as a function of position. So what I can see in the graph is that pretty much at every instant, the force is continuously changing. So it starts at 0, then it goes to about 1.0 newtons here, then to 2, and then somehow at this position, it's being subjected to a bunch of simultaneous forces from 2 to 4.0 newtons, and then it's decreasing over time. So again, our equation on its own is not enough to actually handle that. However, there is something we can do with the graph here that will calculate the net work on the object. And this is where we want to use a force displacement graph. We apply it, a force displacement graph, when the force is variable over the displacement. There are two things we pretty much can get from a graph. One thing is we can get the slope, and the other one is we can get the area. If you calculated the slope of this graph would have units that would be rise over run. So the rise would be your units on the y-axis, which is newtons, over run, which would be divided by the units on the x-axis, meters. The units newtons divided by meters is not the unit for a joule for work. So the slope doesn't mean anything on this graph. If you did an area calculation, so you have a bunch of you have a couple of triangular sections here. You take like the height, which would have units of newtons, and you multiply by the base of your triangle, which would have units of meters. And yeah, you divide by 2, but that's not important for the units. And it turns out a newton times a meter is equal to 1 joule. Therefore, it's the area under a force displacement graph that is going to yield the net work that is done on the object. And I worded it a bit funky here. So I said the area between the function and the x-axis is equal to the net work done on the object. So what this means is you always go from like your graph to the x-axis. So if your function's above the x-axis, then you calculate the area going downward. If on the other hand, you had a graph where you had a line below the x-axis, then you would go from the function to the x-axis. In this case, it would be up. And I should point out that if you get work below the x-axis, the work would be negative. And negative work has nothing to do with direction. It just means that the object's losing energy. If you have an area above the x-axis, that means that your work is positive. And if positive work is being done, then energy is being transferred into the object. All right, let's look at a couple of examples. So I have a weightlifter is bench pressing a bar whose mass is 110 kilograms. He raises the barbell a distance of 0.65 meters above his chest and then lowers the barbell the same distance. The weight is raised and lowered at a constant velocity, and I want to do the following things. Okay, let's do one part at a time. So the first one is I want to determine the magnitude of the applied force that's acting on the barbell. Well, we're calculating a dynamics quantity, so a force. So a good starting point here would be, yes, to go to a free body diagram. So if we draw the barbell, let's represent it with a rectangle, and I complete the free body diagram. Well, you'd have the weight of the barbell that's down. So we can call that Fg. And it doesn't matter whether you're pushing the barbell up or you're lowering it. You would either be exerting a force up, or you'd be supporting the bar up as it's being lowered. So in either situation, your applied force is also going to be up. So FA is up. There's no reason to draw a mass acceleration diagram here because it tells me that we're moving at a constant velocity. If we move at a constant velocity, that means that my acceleration is equal to 0. Well, let's write down an equation of motion now. So let's look at the sum of the forces in the vertical direction. And because we're moving at a constant velocity, we're in a state of dynamic equilibrium. And if we're in a state of dynamic equilibrium, that means that our forces are balanced. Expand the equation of motion. FA points up, therefore it's positive. FG points down, therefore it's negative. And then, let's expand this a bit further. We'd have FA minus, well, FG is m times g, is equal to 0, which just tells me that FA is equal to mg. Plug the numbers in. Barbell has a mass of 110 kilograms times the magnitude of the acceleration due to gravity, 9.81 meters per second squared. And if we calculate this to 3 significant digits, I believe we get a value of 1.08 times 10 to the third newtons. That's a 3. (1.08 times 10 to the third newtons. So that's part A. Now let's go to part B. So in part B, I am lifting the barbell. The important thing when doing a work calculation is that you need to get the angle correct. So I'm gonna identify what direction my different vectors point. When you're lifting the barbell, your displacement is up. Barbell goes up. And when you're lifting it, you're clearly applying a force that is straight up. So we have FA. Well, what's the angle between these two vectors if they both point in the same direction? They would be 0 degrees. Now let's calculate the work. So the work would be equal to the magnitude of the force multiplied by the displacement multiplied by cosine of theta. I'm going to add a few subscripts to this equation. It's got to be specific. Work done by what? Work is always done by some kind of a force. So I'm going to write down WA. WA means the work done by an applied force, which would be equal to F. Well, what force is that? The applied force. Therefore, whatever the subscript is on the F, that should match the subscript that you have on the work. And you do need to clarify this. Again, whenever we speak of work being done on an object, it's work done by a specific type of force. Okay, let's plug the numbers in. So from the previous part, we had the applied force magnitude as 1.08 times 10 to the third newtons. Excuse me. We're lifting it by 0.65 meters. By the way, that was a really loud sneeze if you're wondering what that was. Times cosine of 0 degrees. And then I'm just going to add another subscript here to clarify I'm calculating the work done in lifting. So I'll say WA lift would be equal to, well, if both the displacement vector and the applied force point in the same direction, we're going to get positive work. So this would be positive 7.0 times 10 squared, and we have our combination unit is a joule. Okay, so that's part B. Part C, we're now going to lower the barbell. When I lower the barbell, my displacement is now going to be down. But even when you're lowering the barbell, you're still supporting the barbell. So you'd still be applying a force upward. So in this case, if you have two vectors that point in completely opposite directions, what's the angle between them? Well, it'd be 180 degrees. Let's go ahead and calculate the work again. So we could say the work done by an applied force is equal to the magnitude of the applied force times the displacement times cosine of theta. Plug the numbers in. So we have 1.08 times 10 to the third newtons multiplied by 0.65 meters. Everything's the same so far. The only thing we're going to change is the value of theta. Cos of 0 is positive 1. Cos of 180 is negative 1. Therefore, the work done, and I'll write down in LOW for lowering, would be equal to the same number, just the opposite sign. So negative 7.0 times 10 squared joules. Again, if work is positive, you're putting energy into the object. If work is negative, then energy is being removed from the object. It has nothing to do with direction. Again, negative work does not mean it's going down. It just coincides with that in this problem. Okay, D wants me to calculate the net work done on the barbell. I'll say specifically net work done by the applied force. So maybe we'll clarify that. Net work done on the barbell by the applied force. Okay, so we can say sigma for net or sum. So the net work done by an applied force would be equal to the work done by the applied force in lifting plus the work done by the applied force in lowering. Therefore, this would be equal to positive 7.0 times 10 squared joules plus, in lowering, it's negative work, so negative 7.0 times 10 squared joules. And then the net work done by the applied force would just be nothing. Overall, if you lift then lower, you have no displacement at all. And if you have no displacement and you're applying a constant force from like start to finish, you don't end up doing any work at the end of the day. Whatever you put in ends up getting lost. Second example, I have a 50 kilogram crate is dragged across the floor by an applied force of 200 newtons at an angle of 40 degrees from the horizontal. Tells me I'm dragging the crate by 5.0 meters, and the opposing frictional force is 60 newtons. So let's calculate the work done by the applied force, work done by friction, and then the net work done on the crate. Okay, so we'll start off by identifying the direction of our vectors. So in this one, your displacement vector is towards the right. Box is being dragged towards the right. This time around, though, I'm applying a force at an angle. So we have FA, and then I will just write this down as theta. So the work done by the applied force, WA, would be equal to FA times D times cosine of theta. Really, what the cosine of theta is doing is just forcing you to take the parallel component of that applied force, because that's the only part that actually does the work. Okay, let's plug the numbers in. So the applied force had a magnitude of 200 newtons, multiplied by the distance, which is 5.0 meters, multiplied by cosine of the angle is 40 degrees. And because there's at least a component of the applied force that points in the same direction as the displacement vector, we're going to get positive work. And also because theta is less than 90 and greater than or equal to 0. So this is going to give me a number that's positive 7.7 times 10 squared joules. That's a 2. Okay, B, Wants me to determine the work done by the frictional force. Okay, so for this one, the displacement of the object is towards the right, and your frictional force is always in direct opposition to the direction that you are moving, or more specifically, the direction of your velocity. Okay, so angle between these two guys, well, it'd be a 180 degrees angle. So the top right here, it was 40 degrees. And in this one, it's a semicircle. So that would be 180 degrees. Okay, now I'm going to change the subscripts here. So I'm going to say the work done by friction, so WF, will be equal to the magnitude of the force of friction multiplied by the object's displacement multiplied by cosine of theta. Plug the numbers in. The frictional force has a magnitude that is 60 newtons multiplied by 5.0 meters multiplied by cosine of 180 degrees. And then the work done by the frictional force would be equal to, well, cos of 180 is negative, so then you just be going 60 times 5, which would be 300. And to two significant digits, we're going to turn this into negative 3.0 times 10 squared joules. So once again, the positive work means the applied force is putting energy into the object. The negative work means that the friction is causing the object to lose energy. And then C, to calculate the net work done on the object, we're just going to add these two work quantities together. So sigma W would be equal to the work done by the applied force plus the work done by friction. So that would be equal to positive 7.7 times 10 squared joules plus negative 3.0 times 10 squared joules. And then I'm going to get a net work that would be equal to positive 4.7 times 10 squared joules. So even though friction was causing the object to lose some work, we put more energy in due to the applied force than we lost due to the force of friction. Therefore, at the end of the day, my work is still positive. Okay, so that's it for this lesson, and you can complete the work hand-in assignment. And in the next lesson, we're going to talk more about different forms of energy, and I'll talk to you then.